Today we're going to talk about exponential growth. Exponential growth and decay. So exponential growth or exponential decay is what happens when our data increases exponentially or decreases exponentially. So the exponential function for an exponential growth or decay looks like this. F of t, so we're going to use t instead of x because for exponential growth and decay, we're talking about a period of time. So instead of x, we're going to have t, where t stands for time. So f of t is equal to a times 1 plus r to the t power. So, important information to know is a represents the initial amount. So, for example, if you have a pond where the bacteria in the pond is increasing every year, the pond had to have an initial amount. So we could say that at the very beginning there were 2 million bacteria in the pond. So our A value would be 2 million. So again, A is whatever your initial amount is. And then this 1 plus R, this is going to represent the growth factor. 1 plus R represents the growth factor. Now, the growth factor is 1 plus whatever the growth rate is. So R represents the growth rate. So your R is usually going to be a percent. So for example, your growth rate might be 50%. So if your growth rate is 50%, we can't put 50% and add that to 1. We have to make 50% a decimal first. And so it would be 1 plus 0.5. Well, 1 plus 0.5 is 1.5. So you might not always see your growth factor as 1 plus a number. Your growth factor is just going to be one number because you're going to go ahead and add the 1 plus the R. So if you ever want to figure out what your growth rate is, you would have to subtract 1 to figure out what your growth rate would be. And then, of course, the t is what our x value is, right? Our t is our variable. T stands for the time. So our growth rate is very, very important because if our growth rate is bigger than 0, so if r is bigger than 0, then that means that we're growing, that would be something like 100%, 120%, 150%. That means what the original is plus way more. So that means we're growing. So anytime you have r greater than 0, we have exponential growth. And by the same idea, if you have an r that is less than 0, it has to be greater than -1, you're going to have exponential decay. Because if you have something like 50%, that means 50% of the original. If you have 25%, that means 25 of the original. So those are all the important information that you need to know for exponential growth and decay functions, right? We talked about the A and the R and the growth factor, which is 1 plus R. So let's go ahead and see if we can get some examples done. We're going to do example 1. And we're going to start with example 1, part A, which is f of t is equal to 500 times 1 minus 0.75 to the t power. And so the questions say, well, identify the initial amount. And remember, initial amount is the A value. It's the value before the parentheses or before the growth factor, before the exponent. So the number in front is 500. So our initial amount would be 500. And then it wants to know, well, what's the growth rate? Remember, growth rate has the word rate in it. So we're just looking for the percent. We're just looking for your R. So your R is negative 0.75. So as a percent, that would be negative 75%. Okay? And now remember, your growth factor is 1 plus R. Your growth factor is 1 plus R. So what we have to do is we actually have to do the math. What is 1 minus 0.75? Well, that would be 0.25, or it would be 0.25. So our growth factor would be 0.25. Okay, and then it wants to know, well, is it a decay, an exponential decay, or an exponential growth? Well, since this is minus, remember, if our R is negative, if it's less than 0, then we have an exponential decay. So we have a decay. All right, let's keep going. Let's do part B of example 1. And this time we have y equals 100, 1 plus 2.5 to the x power. Okay, so our initial amount is the number before the exponent, so that would be 100. And then our growth rate is what we're adding to 1. So we're adding 2.5 to 1. But remember, we want to make it a percent, so that would be 250%. And then our growth factor is when we add 1 and our growth rate. So 1 plus 2.5, our growth factor is 3.5. And then now we need to answer, is it a decay or a growth? Well, if we're adding 250% every time for every x, that means that we're going to have a growth, exponential growth. All right, let's do part C of example 1. So this one says f of d equals 2 to the d power. So don't get confused because we're using a d instead of a t or an x. That's okay. We know that d is our variable because it's saying f of d. So first, what is our initial amount? Remember, the initial amount is the number that comes before the exponential. I don't see anything in front of this 2 to the d power. But remember, there's always an invisible times 1. So our initial amount is actually 1. Now we need to do our growth rate. So our growth rate is what we're going to add to 1. I don't see anything added. I just see a 2. But remember, this 2 is your growth factor. So your growth factor is 1 plus r. So if your growth factor is 2, that means that 1 plus r is equal to 2, which means r is equal to 1. So your growth rate is 1, but if we write it as a percent, that would be 100%. And then next question, what is the growth factor? We already said that that would be 2. So is it an exponential growth or an exponential decay? Well, since our r is greater than 0, we have an exponential growth. All right, last part for example 1, part D, we have y equals 10,000 1/2 to the x power. So our initial amount is the number that comes before the base and the exponent, which is 10,000. So our initial amount is 10,000. So our growth rate, to figure out our growth rate, we first have to know what our growth factor is. So our growth factor is 1/2, okay? So 1 plus r is equal to 1/2. So if we want to figure out what our rate is, we have to solve for r. So r is 1/2 minus 1, so negative 1/2, or negative 0.5. Okay, so our growth rate is negative 0.5, or negative 1/2, which as a percent is negative 50%. So our growth factor, we already said, was 1/2. And then is it a decay or a growth? Well, since we're subtracting 50%, since our growth rate was negative, it's going to be a decay. Okay, let's do another example, and this one's more of a word problem. Okay, so we have a basketball tournament, and it's a single elimination tournament. So every time a game is played, one team is going to be eliminated, right? So since it's a single elimination, that means that half the teams are eliminated every round. So they want to know this. They want to know, write an exponential function representing the number of teams left after each round if the term begins with 64 teams. So again, we're doing example 2. And they told us, so let's think about it like this. First of all, let's write what a general exponential growth or decay function looks like. It looks like this. F of t equals a 1 plus r to the t power. So they tell us in part A that we're starting with 64 teams. So we know that A is 64. And then we also know that we're losing half of the players each time. Half is the rate. So we have 1 minus half. Okay, and then we just have to the t power. That's part of our function. Okay, so now we have our function. Okay, we can actually simplify this and say, well, f of t equals 64. 1/2 minus 1 is 1/2. So we can actually say this. This is actually more simplified here. But part B wants to know, well, how many teams are left after 3 rounds? So we're going to plug in 3. So 64 times 1/2 to the 3rd power. Okay, well, we can do the math. 1/2 to the 3rd power is 1/8. And then 64 times 1/8 is going to give us 8. So there are 8 teams left after 3 rounds. And so part C in example 2, the question is, well, graph this function and determine how many rounds it takes to determine a championship. A champion. Well, a champion is going to be when there's only one team left. So we want to keep going until we only have one team left. So let's go ahead and make our chart. So we're going to have t, and we're going to plug t into our f of t equals 64 times 1/2 t. We're going to plug that in, and then that's going to give us our f of t. So again, we're trying to figure out the f of t when there's only one team left. So let's start with 0. So we get 64 1/2 times 1/2 to the 0 power, anything to the 0 power is 1. So 64 times 1 is 64. So 64. So at the very beginning, before there are any games played, 0 game played, there are 64 teams. Well, what after one round? After one round, let's see, we do 64, 1/2 to the first power. 1/2 to the first power is just 1/2. Half of 64 is 32. So after one round, there are 32 teams left. What about after 2 rounds? So that's 64, 1/2 to the second. 1/2 to the second is 1/4. So 64 times 1/4 is 16. So after 2 rounds, there are 16 teams left. After 3, well, we already calculated that in part B, there are 8 teams. After 4 rounds, that would be 64, 1/2 to the 4th power. So 1/2 to the 4th power is 1 over 32, or I'm sorry, 1 over 16. And 64 times 1 over 16 is 4. So now we're up to 4 teams. We still have to keep going because we only want 1 team. So 64, 1/2 to the 5th power, which is 64 times 1 over 32. So 64 times 1 over 32 is 2. Almost there. So let's do 6 rounds. So that's 1/2 to the 6. So we get 64 times 1 over 64, which gives us 1. So this tells us that after 6 rounds, there's only 1 champion. So let's go look at what the graph looks like. At 0, we had 64. Let's go ahead and count by tens. So here's 10, 20, 30, 40, 50, 60, right? So, 70, okay. So at 0, we had 64. At 1, we had 32. So 132. And at 2, we had 16. At 3, we had 8. At 4, we had 4. At 5, we had 2. And at 6, we had 1. So this is what our graph looks like. So the answer to the question, because the question was, how many rounds does it take to determine a champion? Our answer is 6 rounds, right? Because after 6 rounds, we only have 1 team left. That's our champion. Okay? Notice what this graph looks like. The graph is getting closer and closer and closer to 0. It is decreasing, which is what we call an exponential decay. In an exponential decay, your graph will decrease. Notice that your R is negative, right? And remember, when an R is negative, we have an exponential decay. So there's so many different ways on how you can tell if you have an exponential decay or not. There's the graph, and there's also the R. All right, let's do another example. Example 3. So for example 3, we have a mold culture. And we have 5 grams we start with. We start with 5 grams of a mold. Okay? And it's increasing in size by 200% every day. So we need to write an exponential function to model this growth. And then we also want to find the size after 1 week. Okay, so start with general. F of t is equal to a times 1 plus r to the t power. So they tell us in the problem that our initial amount is 5, so that's our a. And then they also tell us that our rate is 200%. So as an r, that would be 2. So that means that our function is f of t equals 5 times 3 to the t power. So if we want to know what the size is after 1 week, remember it's increasing by size by 200% every day. So how many days are in a week? 7. So that means we need to evaluate for t equals 7. So we'll have 5 times 3 to the 7th power. So when you calculate this in your calculator, it's very important that you don't put 5 times 3 to the 7th power. You need to make sure that you do 3 to the 7th power first and then multiply by 5. So 3 to the 7th power is 2,187. So 5 times 2,187 is 10,935. That's how many grams of mold you have after 1 week. Okay, so let's talk about something that is really useful to us for exponential growth and exponential decay. We're going to talk about compound interest. So interest is something that you collect, that you get in your account at the end of the year. Okay, so you can have annual compound interest. You can also have semi-annual, which is twice a year, quarterly, which is 4 times a year, or monthly, which is 12 times a year. Or you could have daily, which is 365 times a year. You have to be careful when you determine interest rate because you have to divide the percentage rate by the number of periods in a year. So for example, if your interest rate is 6% and you want to find out what your annual percentage rate is, so here's your rate, but you want to know what is your annual percentage rate, which we usually call APR. So your annual percentage rate is not the same as your rate. Your rate is just 6%. However, if you have to divide that by the number of periods in a year. So for example, if you're compounding monthly, that means you are compounding 12 times a year, which means there are going to be 12 periods. So your annual percentage rate is your rate divided by your periods. So if you're doing monthly, which is 12 periods, it would be 6% divided by 12. Which would give you 0.005, which is actually 0.5% every month. So for the whole year, you get 6%. But because you're compounding in monthly, so you have 12 periods, you're doing 0.5% every month. Okay. So a compound interest has a formula, and it's super easy. As if you can know the formula, then you can pretty much plug everything else in. Okay, so let's go ahead and learn what the formula is. It's A equals P times 1 plus R to the X power. A, which is sometimes called f of x, that's going to be the account balance after t number of years. okay? And then you have P, which is kind of very much like your A. This is going to be your principal amount. So how much money did you start with? And so R is going to be your periodic interest rate, okay, which again, remember, is APR, which is equal to your rate over the number of periods.